Okay, let's start. So we have been looking at noise in all our circuits, and we saw that in all the circuits that we have, the noise generated by all the noisy elements at the output that can be modeled as though the network is noiseless and the noise is arising due to two sources, one voltage source and one current source at the input. Okay, this is called the input referred noise. And in particular, if the input impedance is infinite, there is no requirement for this current. So the noise can be modeled only using a voltage source. So, and this is nice because in all our amplifiers and in all our OTAs, the input was given to the gate of some MOSFET. So to model the effect of the noise, only equivalent voltage source is enough. And also for a MOSFET, although the noise in this drain current is ideally modeled using a parallel current source, we saw that if we don't consider the gate capacitance, which translates to having infinite input impedance, this noise can also be modeled using an equivalent voltage source at the gate. So the drain current has a power spectral density 4 kT gamma gm. So this will have a power spectral density 4 kT gamma by gm. And this comes quite handy because again in all the amplifiers we have the input is given to the gate of a MOSFET. So if you were to find the effective input referred noise voltage for the overall circuit, it's obviously going to have contributions from each noise source, and the contribution of this input transistor to the input referred noise is straightforward. So if you had to find the input referred noise power spectral density, the contribution due to the input MOSFET, say it's M1, that's simply 4 kT gamma by gm, and then you will have other contributors. Okay, cool. And in the last class we also made one observation. If you have a cascode where the input is applied here and the output is taken somewhere at the drain here, we saw that the noise due to the cascode device, what is the noise contributed by the cascode device? If I assume this has infinite R0, it was basically 0, because if this guy is infinite, this noise current simply keeps circulating and nothing comes out. Okay, so that's another important observation. If you have a cascode structure, the noise of the cascode is very insignificant. Great. So now we have seen noise in basic amplifier stages: common source, common gate, common drain. We also looked at cascode. So let's start looking at all our OTAs. So I'll start with the 5-transistor structure. So we have the PMOS current mirror, the NMOS diff pair, and the current source. I'll label the transistors. So these are the inputs V1 and V2, and this is our output, right? So let's try to find the input referred noise here. So again the logic is same. We'll short the inputs, find the short circuit output current due to each noise source, and then divide it by the gain to refer it to the input. So first let's find the gain, right? So what is the transfer function from the output current, from the input difference to the output current? What is this? GM1. It's GM1. It's basically a short circuit GM, so it's GM1. So hopefully that is clear. So now let's try to find the noise contribution through to each noise source. So again I'll short circuit the output here, and the inputs are also grounded like this. So here I have basically 5 transistors. So let's say M0, M2, M3 and M4. So I'll try to find the noise due to each, right? And I'll refer it to the input, and this is simply I out by GM1. So what do you think is the noise contribution due to the transistors M1 and M2? If I refer it to the input, what is the input referred noise contribution due to M1? it's simply the same. Okay, see, one thing is, in all the OTAs we have differential input. The output is single-ended or fully differential. So the this noisy OTA, we are trying to model it using a noiseless OTA in series with some voltage source that generates noise. Again, this voltage source can either be at the non-inverting terminal, or we could have it at the inverting terminal, or anything, or you can have both also. For all that matters, we are interested only in the difference between these two guys. So it doesn't matter where you refer it. Okay. And yeah, so the input referred noise due to M1 is simply the input referred voltage of the transistor itself. So I'll just write it as Vn1. Okay. So what do you think will be, if I, let's say, try to compute the short circuit output current due to M1, what do you think that will be? I mean, the voltage is basically Vn1, that's straightforward. Basically, because I am referring it, I'm modeling the noise like this. If I have to find the short circuit current due to Vn1, what do you think that will be? Gm1 times Vn1. Okay. Again, the difference between the two voltages times Gm is the output short circuit current. So I'll just write it like this. It's In1. It's basically Gm1 Vn. Fine. What about noise due to M2? It is same. We directly can club to the input. It's Vn2. I'll just write it as In2. So these two are straightforward. So okay. Let's see if I can copy it. So let's now look at the other transistors. I'll start with the tail current source M0. Let's say this is the noise current IN0. Again, for noise calculations, we'll assume all the R0s are infinity. Okay. So now what do you think will happen to this current IN0? It is getting injected at this node. So what will happen to the current? It will split. And how does it split? It will split equally, right? Because the impedance looking here, both are 1 by Gm. Okay. So the current is going to split equally. So the current in this branch is In0 by 2. So here also it gets split equally. Right? Now the current flowing in M1 also flows to M3 as I marked here. And I know this guy is a current mirror. So whatever current is flowing in the diode connected transistor will get copied onto the other side. So this is also In0 by 2. So what is the final output current? 0. Okay. So this doesn't contribute to noise. Again, this is another important observation. If in these kind of differential amplifiers, any noise that you are injecting into the common node like this, right? So that will not appear if you consider the difference. This is basically responding to the differential input, isn't it? Okay. As long as we are looking at the output, which is dependent on the difference between the inputs, any noise that is getting injected in these common nodes, that usually doesn't appear at the output. Okay. So this is done. So let's move on to the noise sources. Basis. Okay. Yeah. Now let's look at the noise due to M3. I'll model it using a current like this. Okay, again VDD is incrementally short, so probably I'll redraw it slightly differently. Okay, N3. So now where do you think this noise current IN3 will flow? It has two parts to go, either down or up. It will flow towards towards the upper side, right? Because I have assumed R0 to be infinity. Even otherwise, a very small fraction of the current will only flow down. All the current will essentially go to the PMOS. And now if you think about it, I mean, this is open circuit for now. You have a current source getting injected into diode connected transistor, classic current mirror configuration, and that same current will have to be mirrored here, right? So this is my IN3. Okay. So what is the output short circuit current now? I mean, can it look at the signs carefully? It doesn't matter, but it doesn't matter, but it always pays to be minus IN3. Okay, so if I refer it to the input, it's going to be minus IN3 by GM. Fine. So let me scale this there. Okay. Now final noise contributor is M4. So this IN4. So now again this current can flow here or here. Where do you think it will prefer to flow? It flows to the short circuit. So IOut is basically IN4 directly. Okay. So this is IN4 by GM. That's all. That's fine. So let me copy these guys and let's write the fast spectral density. So now my Vn in is basically Vn1 plus Vn2 minus IN3 by GM1 plus IN4 by GM. So if I try to find the fast spectral density of this input referred voltage noise, what is that? Vn1 has a fast spectral density 4 kT gamma by GM1 plus it is the same. So both GMs are equal, so it just 2 times this. Okay, plus yeah, 4 kT gamma GM3 is the PSD of IN3 by GM1 square. Again, it have the same for IN4 also, it scales by 2. Okay. So I will simplify it like this: 8 kT gamma by GM1. I'll have 1 plus GM3 by GM. Okay. So this again fine, because the noise due to the input transistors, they simply get added. They are directly appearing at the input, and the noise due to the current mirrors, they are getting scaled by this factor GM1 square. Okay. So now if you had to reduce the noise, of course the input stage you can't do anything because its noise directly comes. For the current mirror, probably you can try to keep GM of the current mirror to be smaller than the GM of the input transistors. Right. So let's say you try to keep, if you try to reduce GM3, and note that the current flowing through the transistors is fixed, bias current, right? If this is I0, the bias current is fixed to I0 by 2. Okay. So if you are trying to reduce GM3, keeping the bias current fixed, so what does it mean if the GM3 reduces for a fixed current? Right? Because GM3 I know is basically twice the drain current by the overdrive voltage. If GM3 drops for a constant ID, which means I'll have to have a larger overdrive voltage. Okay, but if I keep increasing the overdrive voltage for the PMOS transistors, so what will happen to this voltage? This voltage, that will keep on decreasing, and of course if it keeps on decreasing, this transistor may go out of saturation. So of course there is a trade-off. Okay. So design process is always about trade-offs. You try to do something, something gets affected, so you always try to find some sweet spot. Okay, cool. So now parallelly we'll also try to look at the effect of mismatch. Now if you recollect, in all our transistors or in all our amplifiers, we have this differential pair, and in transistors what kind of mismatches we have usually? What are the two things that can be mismatched? Yeah, one is the threshold voltage and other is beta, right? And as I mentioned, usually this is the dominant mismatch contribution, so we'll neglect this guy. And if you have mismatch in the threshold voltage between two transistors, how can I model it? Yeah, always remember that the transistor functions on VGS minus VTH. If there is any change in the threshold voltage, that can be modeled as an equivalent change in the gate to source voltage. I can consider that the threshold voltage is same, but the gate to source voltage is different, right? So here, if these two guys have different threshold voltages, the easy way to model it is to assume that they have the same threshold, but let us say there is some delta Vt added here at the gate. Okay. Now, if this is the case, we saw that, let's say, ideally, if we have an OTA, if both the inputs are grounded, what do you think the output should be? Output should be 0. Even the short circuit current, same thing, should be 0, right? But now I see that if there is a mismatch here, what do you think the output current will be, short circuit output current? It will be some non-zero quantity, okay? So if I try to sketch the characteristics of this OTA, ideally it should have done something like this, but now it might be here or here, and this is what introduces offset. Okay. And just like in the case of noise, we'll model this offset as follows. So this is where we have mismatch. We'll assume that the OTA itself does not suffer from mismatch. That is, all the transistors here are matched. Okay, but the non-zero output current for a zero input is arising because we have an effective voltage source at the input. Okay, so this is the final stuff. This is the final OTA. So we'll assume that the offset is arising due to some voltage source that I have added at the input, and this is the input referred offset voltage. Okay. And the procedure to find this input referred offset voltage is identical. You first take the transistor with mismatch. For zero input, you find what is the short circuit current, some non-zero quantity, and that quantity you divide it by the transfer function from input to the output. That's all. Okay. So let's do this calculations for our 5-transistor OTA. Let me see if I can copy paste this. Yeah. Well, let's look copy paste this. So here we have two possibilities for mismatch. Which transistors can be mismatched here? M1, M2 can be mismatched, and then M3, M4. Okay, we have only two possibilities. So again, to find the effect of mismatch, first I'll assume that we have zero inputs, right? And the mismatch in the threshold voltage is what we'll consider. And any mismatch in the threshold voltages of these two guys, I'll model it using a voltage source delta VTH12. Similarly, for M3, M4, I'll model it using another voltage source delta VTH34. Okay. So now my goal is to find the output current due to these two guys divided by the transfer function from input to the output, and the transfer function from the input to the output is already known. It's a short circuit GM. So that is fine. So the only goal is to find the current now. Let's quickly do that. So here again I have two input sources. So I'll use superposition and find the contribution due to each of them one by one. So let's say this is I out again. This is the input referred offset. This is basically I out by GM1. So first let me consider only the mismatches in M1, M2. So now this is the case. So what do you think the short circuit output current will be? This guy is 0. If I assume that this is negative and this is positive, this is delta VTH12. So the difference input is delta VTH12 or minus delta VTH12. So what will be the short circuit current? GM times is input difference. It's GM1 times delta VTH12. Okay, so if I refer it back to the input, it's again similar to the case with noise. Any mismatches in the input transistors, they directly add to your input offset, right? Why do you want to be 2 times? The mismatch in these two guys is modeled by 1 voltage source. Okay, let's calculate it. We already found it, right? If we have two, guess this. Let me take some general inputs, right? That might be even simpler. I'll assume this is V1 and V2, right? And if all R naughts are infinity, what can I say about this tail voltage? No, why is it 0? Average of the two? Yeah. So what is the incremental current here? GM times V1 minus V2 by 2. I'll just call it VID by 2. What is the current flowing here? That is the same. So now this current will also get mirrored here, right? So GM1 VID by 2. This also GM1 VID by 2. So the output current will be GM1 times VID. Right? Okay. Is that fine? Okay. So if this is done, let's move on to the mismatch due to M3, M4. So erase this guy. So now I have, oops. Let's assume this is minus, this is plus. Yeah, so what do you think the short circuit output current will be now? Yeah, why is that so? Yeah, okay, so any other result? Okay, let's see. This is the quiescent current I0. Again, this current is going to split equally like this, right? So what will be the quiescent voltage here? Source to gate voltage of the transistor at I0 by 2. Okay. So now even if there is a change in delta VTH3, what do you think this voltage will be? The current in this transistor is basically fixed to I0 by 2, right? So even if I apply an increment here, this voltage, do you think it will change? Sorry? No, incrementally what I am saying is the difference between these two is delta VTH, but this guy will be fixed to that voltage, because see, here the current is fixed, right? It's fixed by this guy. Okay. So incrementally this will be short. So incrementally this is short. So the incremental voltage applied to the gate of M4 is delta VTH34. So what will be the short circuit current? It's GM3 or GM4 times delta VTH34. Again, the quiescent current here will also be I0 by 2. Okay. So now you see, right, here the total current is this GM3 delta VTH plus I0 by 2. The current flowing down is I0 by 2. the difference will flow out. So again, this is not actual short, this is only incremental short. So remember that this is only incremental short. Is that okay? So due to M34, it is going to be GM3 times delta VTH34. If I refer it to the input, it's GM3 by GM1 delta VTH34. Okay. So again, as with any random quantity, it doesn't make sense to directly look at the value of this offset voltage. What we are interested is in the standard deviation. So first let me write the variance. If I write the variance of the input effort offset, what is that? Yeah, okay, first let's contribution of this guy. Yeah, sigma square delta VTH of 1 2 plus GM3 by GM1 square delta VTH3. Again, the result you get is very similar to what you had for noise, right? So I mean, you know that sigma VTH is inversely proportional to the area or square root of the area. So this becomes A VTH of the NMOS by WL of the transistor 1 square A VTH of the PMOS and this both 1 2 and 3 or 4 anyway. Okay. So now if you are to reduce the input effort offset for the transistor, I mean if the dominant contributor is the mismatch in M1 and M2, what is the solution? We have to increase W and L. The only solution is to increase the area, right? And that's a general rule. If you want to reduce mismatch, you keep increasing area because all the quantities are inversely proportional to the area. Whereas for the transistors M3, M4, you have an additional thing to play with, the ratio GM3 by GM. Okay, cool. So if this is done, let's move on to the next OTA. So after looking at the 5-transistor OTA, what is the next configuration we looked at? We looked at the Cascode, and first we saw telescopic Cascode. So let's quickly do noise and offset for this guy. So let me label this M0, M1, M2, M3, M4. Okay. So first let's look at the noise of this guy. So again, we'll find the contribution from each transistor to the output. And before that, what is the transfer function from the input difference to the output current? It's same, short circuit GM, which was GM1. In fact, in all our OTAs, the short circuit GM was the GM of the main diff pair, right? So let's find the noise. I'll short the inputs. So now I have a lot of transistors, M0, M1, M4. Let's see for each of them. Okay, let's start with the easy ones. What is the contribution due to M1 and M2? Shorting the current. What is the contribution due to the transistor M1 to the input referred noise voltage? Yeah, it's basically the noise of that guy itself, and current is same as IN1. Okay, so similarly for M2, it's VN2 and IN2. Fine, that's straightforward. So now let's look at the noise contribution due to M0, IN0. So what do you think will happen to this current now? it will take the same path as before, right? So you'll have IN0 by 2 flowing here, IN0 by 2 flowing here. So the current flowing in this branch will get mirrored here. So we have the current, this is I0 by 2. So the same current will get mirrored here. Oops, I think direction is wrong, sorry. So this is half the current, this is also half the current. So the current is flowing in this diode connected device, that is mirrored here. So the final output current is 0, same as before, simple. Okay, so this is 0. Now let's look at M3, M4. So for M3, again the noise I am modeling it like this, because this is short. So where do you think this current will flow? It has two parts, up or down. Up. What is the impedance looking up? No, but it is looking into the drain, right? Okay, so this is going to have some R0, right? What is the impedance looking down? I am looking into the source of M7. That is going to be the smallest resistance. So basically all the current will flow like this. So current will flow in this impedance here. And what is the impedance here? It's basically diode connection between like this. It will be 1 by gm of transistor M3. Okay. So basically what I am saying is it is same as before. It's also we are injecting the current here now, right? Because that current essentially flows into that node. So this is basically IN3 by GM3. So this voltage is IN3 by GM3. What will be this current? It's minus GM3 times that voltage. Okay. So the current is minus IN3 that completely flows to the output. So this is minus IN3. This minus IN3 by GM. Now let's look at M4. 0. Now similar situation, what will happen to this current IN4? It has two parts. It will prefer to flow down because looking down it's 1 by gm of the transistor M8. So basically all the current will flow, reach the output. Okay. So this is same as before, IN4. And if you think about it, it's very similar to the case in the Five-transistor OTA. There also we had very similar stuff happening. Okay. So now let's look at the Cascode transistors. So let's start with M5, M6. So here the current, noise of this transistor M6, I can model it using either a current source or a voltage source. So let's say I do it with a voltage source. Okay, and remember that these are all incrementally short. Right? These are connected to some bias voltage, they are incrementally short. So I can as well do this. So noise of M6, I'll model it using its VN6. Fine. So because of this guy, what do you think the output current will be? If I change the gate voltage of M6 here, what will happen to the current? Again, I've assumed that all R0s are infinity. Okay. Cascode. So basically this is now an open circuit for us, right? So this open circuit, so what can you say about the current? It will be 0. It's open circuit incrementally. So no current will flow in, small signal current will not be there, right? And I mean, basically, if you think about it, if this is opened, this is now a source follower. If this is Vn6, this will also be Vn6. So incrementally, there will be no current. So yeah, this is M6, M6 is 0. So same way, if I have noise for M5, what can you say for M5? It will be same, right? This again consistent with what we saw for the Cascode, right? For the Cascodes, if you assume the R0s of the main transconducting devices are infinite, there will be no noise due to the Cascode devices. So yeah, so let me. So these are. So 0. Now let's do for M7 and M8. So this is all incrementally short. Let's say Vn8. So what do you think will happen due to Vn8? So again, I have assumed R0s are infinite, so this is open. So if I change the gate voltage here, identical change will appear at the source follower. So IOUT is still 0. Okay. The same thing you can do for M7, that will also be 0. Okay. So again, it is same thing we saw for Cascode. As long as the output resistance of these transconducting devices are infinite, the Cascode devices don't contribute any noise. Okay. So now if you see the total input referred noise voltage is only from 4 transistors, similar to what we had for the 5-transistor OTA. Even the power spectral density will be same. Right? So let's quickly look at the offset now. So how many sources of mismatches are here? I can have mismatches between these guys, these. Okay, I have 4 possibilities. So let's look at that. So first we look at the simple ones. Mismatch due to M1 and M2. So I can model the noise. Sorry, mismatch like this. Right. So what do you think the output current will be? GM1 times this guy, so it's straightforward. So the input referred offset voltage, this is VOS in. This is delta VTH12. It adds up as usual. Now let's look at M3, M4. Delta VTH34. What do you think the current will be due to this guy alone? It's very similar to what we saw before for the 5-transistor OTA. This guy will be incrementally short. There will be no change in this voltage. So this incrementally short, this is short. So it's as though I applied a voltage of delta VTH34 to the gate of M4. The current flowing will be minus GM3 times delta VTH34. Okay. Okay. So now let me look at the other guys. So let me consider the mismatch due to M5, M6. Again, remember that these are all incrementally short. Now if there is any threshold voltage mismatch between M5 and M6, I can model that mismatch by an effective voltage at the gate. So I can add the voltage source to the gate of M5 or M6. So let's say I do it with M6. This is delta VTH56. So what do you think the current will be? 0. It's very identical to the noise case, right? So even due to M5, M6, it's going to be 0. So finally, we'll do the same thing for M7, M8. So I can model the mismatch in the threshold voltage by adding an effective voltage source at the gate of either of the transistors. If I do that, if this changes to delta VTH 7, 8, what do you think will happen to the output current? 0. Identical. So this also. Okay. So now again the input referred offset voltage, if I write the variance, it's sigma square delta VTH 12 plus GM3 by GM1 square. This is basically GM3 by GM1. I made a mistake. So the result is very similar to the Five-transistor OTA. Okay. So this is a nice thing because see now with Cascode I've added 4 additional transistors, but it looks like they are not contributing any noise and they are not adding to my offset. Okay, this is a nice advantage with Cascode, that the effect of these Cascode devices is very minimal. I mean, if R0 is infinity, it's 0. With finite R0, it will be very small. Okay. So we have some time. Let's finish the next configuration. So along with telescopic, we also looked at one other Cascode, folder Cascode. So let me do that quickly. So let's start with the diff pair. So the Cascode is going to be PMOS now, and then I have an NMOS current source. Form the current mirror. So this voltage. So we'll have label it the same way so that there is no confusion. M3, M4. So compared to the telescopic Cascode, we have basically 2 additional transistors here. That's all. Otherwise, it is very similar, right? 8 transistors as before. Just that in the telescopic Cascode, these were NMOS and these was PMOS. Here it's just dual of it. Okay. So now let's say if I try to find the noise. Now can you tell me the effect of noise of each guy? Just the M3. So what do you think will be the noise due to M0? It will be 0. Again, the structure is identical to telescopic Cascode. As long as you are considering only the incremental picture, having an NMOS or PMOS makes no difference, and I am considering R0 as infinity. So incrementally this guy will not play any role. So the results will be very similar. So for M0 it is 0. For M1, VN1, so the current is IN1 basically. For M2 it's also same. For M3, what was the current? Basically same thing, IN3 and IN4. What can you say about the Cascode devices? 0. So all these guys will be 0. So please work it out and verify it yourself. I am just extrapolating from what we saw. Okay. So the only 2 devices to check are for M9 and M10. So let's see that. So let's say this is IN9. So now this current has basically 3 paths. It can either flow here, or say here, or here. It can flow up, left, or down. If R0s are all infinite, where do you think it will flow? Yellow, right? It will all flow down because this is looking up, it's infinite. Here also it's infinite. So all the current will basically flow down. So this will be my IN9. So this current is flowing into the diode connected device. That's a current mirror. So it basically gets mirrored here. So the output current will be same, IN9. or actually minus IN9 if you want to be exact. Okay. So okay, let me erase this quickly and write it. Yeah, let's say now I take IN10. So why do you think the current will flow? It will again flow down, right? Because all the others will be open. So the entire current will actually flow to the output. Okay. So now compared to the telescopic cascode, now the two current sources that we have added, they are directly contributing to my noise, right? And if I write the input referred noise, these guys are identical to as before. So this will be referred as, so if I refer it back to the input, it's IN9 by GM1. This will be IN10 by GM1. Okay. So if I quickly write the path spectral density, so earlier with my 5-transistor OTA and the telescopic cascode, I had something like this: 8 kT gamma by GM1 plus 8 kT gamma GM3, which was divided by the gain GM1 square. Now I have two additional sources. One is IN9, one is IN10, which is also getting divided by GM1. So the path spectral densities of IN9 and IN10, they are same. It is 4 kT gamma times GM9. Okay, I will assume M9 is same as M10, so it's twice, and we have this. So if I write it, it's 8 kT gamma by GM1 and plus GM3 by GM1 plus GM9 by GM1. Okay. So since we have done for noise, we can finish the offset also for this guy. Okay, so can you tell me the effect of offsets for these quickly? Erase this. Yeah. So now for offset, I'll have to consider now one more additional pair, M9, M10. Yeah. So I'll call I out. So due to M1, M2, if I have a delta VTH mismatch, I'll add a voltage source. What will be the output short circuit current? GM1 times this guy, delta VTH12. So if refer it to the input, it's similarly if I have for 3 and 4, I'll have some voltage source here. Again, this will be incrementally short. Okay, so whatever voltage source you apply here, that will result in a current that will flow to the output. So M34, it's GM3 times delta VTH34. So what do you think will be for M5, M6, M7, M8? They'll be 0. I mean, you can please repeat the calculation yourself so that you will get some practice. But the calculations will be identical to the folder cascode case, telescopic cascode case. So these guys will not contribute anything. Okay, because again, incrementally having an NMOS or a PMOS doesn't make any difference. So last we have M9, M10. So let's do that. Ideally, both of them are incrementally short, but we have a threshold voltage mismatch. So let us say at the gate of M10, I am adding a voltage source, delta VTH 910. So what do you think will be the incremental current flowing here? Gate is at delta VTH, source is incrementally short. So this is minus GM10, delta VTH 910. And that current cannot flow here, it will only flow down. Okay. So the entire current will basically flow down. So minus GM10 delta VTH 910. Okay. So if I write the input referred offset, so it will be similar as before. I will have sigma square delta VTH 12. I will have the effect of 3,4 multiplied by GM3 by GM1 square. Okay. Plus you will have additional term sigma VTH of 910 into GM10 or GM9. So the additional current sources that we are adding, they'll add to both noise and offset. Okay. So that's an issue with the folded cascode. But what was the advantage with folded cascode? Yeah, I mean in terms of swing, yeah, I mean if you think about it, please recall the common modes of the input and the output were strongly coupled in telescopic cascode. But the moment you split them like this, the common modes at the input and the output are less coupled. And also most importantly, if you have an NMOS input stage, with a folded cascode, the input common mode can be close to 0. It can be 0 actually. And if you use a PMOS input stage, it can be VDD. So that's the only advantage. So if you have a NMOS input stage, the common mode for the input can be at 0. At VDD. Sorry, I made a mistake. Yeah, you're right. Yeah. Sorry. For NMOS, the common mode can be at VDD. Similarly, for the PMOS, the common mode can be at 0. So that's the only advantage with folded cascode, right? If you don't want a case like that, you are better off using telescopic cascode, because this is adding more noise and more offset. Okay. So let's stop here.